cycles a second. But on the more mundane scale is the spectrum of things we use, the frequency allocations, which is astonishing. Okay, then I showed you a demo, which I don't know if you really had time to really appreciate what it was doing, but what we had actually was a capacitor and an inductor built into a little box. And from that, we peeled off, there was long rods sticking out like this, and what I had over here was, so that's a transmitting antenna. Is this thing here. This is the oscillating circuit that it was creating an 85 million cycles per second, or hertz, radio wave, which is something like the FM band. And it was radiating this, and I was picking it up with another antenna, which had a little lamp on it, right? So, first of all, let's figure out what is the wavelength that this thing is emitting. Okay, so we go back to the formula I more or less wrote up there. So the speed is frequency times wavelength. I'm saying it's 85 megahertz. I didn't tell you how I knew that, but let's see. So the speed of light is 3 times 10 to the 8th meters per second, and the frequency, I'm saying, let's make life easy. Let's call that 100 megahertz. And so 100 mega is 10 to the 6, 100 is 10 to the 2 times 10 to the 6, 10 to the 8th per second. So I divide through, and I get 3, seconds. So I get 3 meters is the wavelength of an 85 megahertz wave. 3 meters, 3 yards, which is what Cal is usually left with on third down. 3, 1, 2, 3. And so the antenna was actually about this long, right? So the antenna was about, in fact, about a half wavelength. The antenna here was roughly 1.5 meters. It wasn't 3 meters, right? It wasn't that long. It was more like that. And the reason is that is a very well-tuned antenna for this wavelength. What you want is actually a wavelength and a quarter over here and a wavelength and a quarter over here. Makes for an efficient antenna on both sides. And you want to radiate that with a lambda over 4, lambda over 4. And I started to show you why that is. And somebody asked me about it. And I think I wasn't doing it as neatly as it should. The way to look at it is that if you have, imagine this. Let me start down here. If I have an oscillator, like that circuit over there, and it's sending out plus and minus signals, let's say it puts out a plus to here, it travels at the speed of light. See, now things really have to take time because light doesn't travel infinitely fast. So it creates a electric field, a dipole field, say that's strong because the dipole moment is like that. Okay, so that's at one moment. Then, a moment later, the electron is driven up to a little further. Let me get a different color here. It's driven up, say, to this point, and the minus is driven down to that point, and you get an electric field from plus and minus, and because it's proportional to the dipole moment, you get a bigger field like this. But in the meantime, this fellow is traveling out at the speed of light, so he's over here. As far as this one's gone up, this one's gone out, because they're both traveling at the speed of light. Then finally, this plus charge may reach the end of the antenna, lambda over 4, and here, and it creates a big field, right? But in the meantime, this fellow has moved out. In the time he went from here to here, he's moved out about to here, so he's about like that. And the fellow that started out here has moved even further, another step like that. So you could keep doing this. You see that the wave keeps moving out. Let me start with another one here. Now the cycle starts to reverse. The charge comes back. Let me continue with this pattern of colors anyhow. Maybe it's come back to the middle here, so the dipole is this way. In the meantime, this fellow has moved out a length, and the I think that one was white, the big one. And then I had a blue one, which was sort of like this, and then I had a little red one like this. So you can see what's happening. I have a wave moving out whose amplitude is a sinusoidal amplitude. And at some point later on here, in fact, the plus will come down to here, and the minus will come down to here. I'll have fields that go this way. In the meantime, all of these fellows have moved all the way out. So you'll have this one is over here, and this one is over here, and this one is over here, and then we have this one over here, and we have maybe another one like that, and then pretty soon it's going to turn around, maybe this way, and then that way, and then another very strong one like that, you see. And so what you've done is you've built up an outgoing sinusoidal wave due to the dipole field moving out. And the feature of this is that the charges are moving up and down, so that the lines that it creates are this way. So that gives you polarization. And in fact, it radiates all around here. If the charge is moving up and down that wire, the field that it creates is a dipole in all directions. So it radiates in all directions, right? But not in this direction. That's very important. I think I did that experiment where I actually put the rod here end to end, and the radiation is bad because the dipole field does not radiate along itself. In fact, what's going on is that the radiation, and this is a very important fact, occurs when charges accelerate. That's the important issue, the important point here that you must grasp. And the argument that you must have acceleration is that, so is it not enough for charges to move? Won't that radiate too? So you think about it and you say, well, so if it radiates, it's actually sending out energy, right? We know that radiation is energy. So if it was sending out energy, everybody would know it. It isn't as though some people think there's energy and some people don't. But suppose I'm here's where relativity comes in a little bit. Suppose I'm going with the frame of reference of this moving charge, and it's moving just uniformly. But next to me, it's stationary. And we know a stationary charge does not radiate. It just has a field. So if in that frame of reference there is no radiation, then in no frame of reference is there radiation. So what you have to have is acceleration. Namely, the charge has to go up the antenna and down the antenna. And that's accelerating because it speeds up, stops, comes back down. Speeds up, stops, comes back. So that acceleration creates the radiation. Yes, ma'am. Well, I'm making a simple model here. I'm imagining a positive charge and a negative charge, which I'm driving with this oscillator source. and I'm just taking a positive charge and I'm sending it up the antenna and down the antenna. And oh yes, they can switch. In other words, you could switch the polarity of that half of an antenna. Yes, in other words, on this part of the cycle, I imagine a plus charge up here and a minus charge down here, and the electric field going plus to minus. Later on the cycle, I mean, this will be a couple of those antennas that I didn't stop to draw. But at some point, my plus charge will be, say, here, and the electric field generated by this dipole will be that way, and so that electric field is then generated in that direction. It starts to propagate. Is that what you're asking? I think it's a little bit simplified model, but it's a basic idea. And it shows you that a couple of important points. One, that by synchronizing the motion up and down the antenna, if you can do it, make it lambda over 4. It turns out that if this length is lambda over 4, it's in perfect step to drive the wave. So, but that doesn't mean you must have lambda over 4, because in some cases, take your radio, for example. If you have an ordinary radio, let's calculate for a, in fact, I think I do it here someplace. This is a little bit spiel on how, for a quarter wavelength thing, the wave is generated. Now, for a radio station, if you look on the dial, you'll see that it says 510 on your radio dial, or 700 on your radio dial. That's kilocycles. So it's actually telling you the frequency. Now, here's a particular tower at 700 kilocycles. So if you figure out the wavelength like we just did, 700 kilocycles into 3 times 10 to the 8th is, the wavelength is 429 meters. Now, if you wanted to have an antenna on your radio that was a quarter wavelength, or half wavelength, it would be about 300 feet. So you have or 700 feet worth of wire attached to your radio. Ridiculous. I mean, you just don't do it. So in radio, we don't have that kind of a tuned antenna. We have a short antenna, but it turns out it's good enough. If you have a strong enough signal, you can hear it. So you could have a very short antenna and it still works, but it's not as good. But if you want to broadcast, then you want to be efficient. So if you're a radio station, you want an antenna a quarter wavelength. So that's what they have. If you go out to the bay, along the Bay Bridge or San Mateo Bridge as well, you'll see these very tall towers, and there's a radio station underneath. And they really have an antenna that's 350 feet long, because the tower is 350 feet long. So there, because they're trying to broadcast a very powerful signal to everybody, they must have a good antenna. We get along because it's awfully inconvenient to have 350 feet of wire. But of course, if you had a ham radio, the guys build a tower because they're trying to pick up all kinds of stuff. So this is typical. Now the thing I wanted to point out, some of you may not know, if you look out, when you go out, if you go out and look over San Francisco, yes, sir, do you have a question? Yes. At the lowest level, they should be considered distinct. On the other hand, we soon will show that they are the same, but go ahead. A lot of things I take back. Right. That's right. That's right. Right, exactly. That's right. That's a good point. And in fact, when Einstein would do a relativity theory, if I ever get to it, we will see that you can see where magnetism arises from electricity. That was a profound insight. But at first, they were very separate, totally separate. Then suddenly they were connected, and now Einstein says they're even more connected than you thought. So in fact, they will be connected. So back to this. Have you not noticed this tower standing over San Francisco? You look out, there's this huge thing. It's actually bigger than that tall building. What's the America building? What's the big triangle building? No, not quite, but the Transamerica. Transamerica is a landmark building in San Francisco. This towers over the Transamerica. If you look out on the hill, it's to the left of the Transamerica. And on top, if you look closely, it is online, these are all FM radio and TV stations that have antenna, something like what I had here, on that tower. And the reason is that FM and TV, you want to have line of sight. You want to be able to see the other antenna because it doesn't go around corners or around the earth very well. So they picked one of the highest hills in San Francisco and put up the biggest tower that they could to broadcast all over the Bay Area. And on top of there, if you look closely, if you can expand your picture here, I don't know that I know how to do that here, but you'll see all the TV stations and the FM stations have, according to the website, PG&E provides them anywhere between 1 million and 2 million watts a day to power the radio stations that are all broadcasting from there. They have a substation that sends them 1 million watts a day, continuous power to drive all those stations. And every one of them has, I don't understand why they don't interfere with each other, but it may be that the antennas are sufficiently different that even though you're standing right, 10 feet away, they don't drive, one guy's antenna doesn't drive the other. It's a little puzzling to me, but maybe they figured it out. Okay, so then I have a little spiel here about how this resonance circuit works, how the energy in this field, when it's charged, transfers over and goes to the magnetic field here, and this produces the oscillation that is eventually brought onto these wires and can send plus and minus charges up and down the wires. This is cute to look at if you have a chance. And I did the demos here, and here is the picture of the overall radio transmitter. And of course, somewhere you will have an antenna to match that. If you can get an antenna that's tuned to the right wavelength, you'll do better. Okay, now polarization has to do with the fact that in a case like this, the wave is oscillating, electric field is oscillating up and down, and we choose the direction of polarization as that of the electric field. So if you have this traveling wave, and this is E, this we will call the direction of polarization. It's the electric field direction. But there's one tricky thing that you should be aware, and that is it's not terribly obvious. For example, if I have a screen like this, and I have polarized radiation, which is coming, this is microwave. Again, doesn't matter what the electromagnetic radiation is, it's still what this is a source of radiation. This is microwave. This is what your cell phone transmission is. And the interesting thing is, again, look at the scale of sizes. This is the receiver end, so I can point it at you with, don't be afraid. But look at the size of the receiver end. You see, it's sort of like that. So the wavelengths that this is generating are roughly like that. This is microwave, few inches type wavelength. And this is a source. It's really mild. It won't hurt me. Crashing over. And the interesting thing about this particular source is that it's a waveguide, which is a pipe. Looks like this. And it turns out that the waves are polarized this way. In other words, electric field is 0 and it peaks like this. You can't have an electric field parallel to metal. So the electric field is like that. And that's the only way it'll get through the pipe. So for example, if I turn this, see the polarization is wrong. The wave is coming in, but it doesn't like to go through this narrow end of the pipe. So that's one thing. Now here's the cunning part. Have you guessed? Now the polarization is this way on here. Which way will the wave go through the screen? Will it go through and it's this way or that way? It's a little tricky. So my first inclination is the polarization is this way, it'll squeeze through. But that's not how it is. Yes, sir? Speak. There you go. Yeah, and that would be bad for trying to get through this. Because if the wave drives the charges up and down, they sort of get used up. They give up their energy to the wires. So that will stop them. So this would be the wrong direction. This will stop them. So the polarizing direction is this one. Strangely enough, here we go. So his thought was, let me put it in this way, and the fields will drive the electrons up and down. But I say that will stop the waves, because you're using up the energy driving the electrons, so it doesn't go through. It's better already. And then if I turn it this way, right? So the fact that now the waves are driving electrons through the narrow end of the wire, and the current really can't get going, and so it doesn't use up the energy of the wave. So in a Polaroid, for example, you should know that when you use Polaroid, if it's a passing direction, it means the molecules are this way. In a Polaroid, the molecules are long molecules, and the current drives the field, drive the electrons up and down the molecules. It uses up the energy. So if you want to get through, you have to put the electric field crosswise to the molecules, right? There's one other trick I want to show you with polarization, and that is that, let's see. It'll be better if I turn the lights out. I'm sorry. Oh, and those who can stay, we can play with that infrared thing. But here, I should. What am I doing? I'm trying to go this way. All right. Yeah. So what I got here is a sheet of Polaroid with the polarizing axis this way. That means the molecules are actually this way. That's how Mr. Edwin Land figured this out. He had long-chain molecules. You just draw out this plastic, and the molecule kind of align this way, and that absorbs the energy. So if you put the thing this way, the light will pass through. So this one is a similar thing, and it's aligned this way. So if I align them parallel to each other, the light gets through both here and so. Whereas if I turn it, now it's crossed, and you see the light that passes through this one is being absorbed by the molecules which are aligned this way. Now the thing I wanted to point out to you is that it matters where if you put in a third polarizer, it matters where you put it. For example, the point is, if these two are crossed, it doesn't matter where I put this. These two are crossed, and the light, no matter what light comes through here, is killed by this one. Whereas if I put it here, below, let's see, you see where it lights up in the center? I can revive it, because the light that passes through this one is tilted by this one, and so it's not crossed to this final polarizer. Think about that, namely that it depends where you put this third one with respect to these two. Okay, I think I have to stop there. And we can play with this gadget here, for those who want to.